CS1 Cascode, CS Cascode with inductive generation to achieve lower noise figure. Of course, their design is more complicated, but here we just try to learn the basics based on Razavi's book, right? Last time I said, okay, when we were using common source, we're talking about common source, just a regular common source, and use the inductive load to match the input impedance. It matched well, but it relied on the coupling capacitor, CF, which is the CGD, the parasitic capacitor of this transistor, to do the impedance matching, which is good. With this inductive load, we have a large headroom, we have a very low noise, and you saw that already in your project, right? Even that what you were doing was not a common source, but a common gate, right? But we still use the inductive load. But the problem is that it might have oscillation. So the goal here are twofold. One is that, right, let's try to use inductive degeneration, which means we're going to put an inductor at the source and the ground, instead of relying on CGD, right? If you don't know what I'm talking about, this is the CF is the CGD, okay? Instead of relying on the CGD, okay? And then later we'll show that we use the cascode. Here is only one single transistor. We're going to have a cascode to isolate it so that we can isolate the effect of the inductor, okay? We had a lot of math, also some confusion. But anyway, the first thing what we did is to look at, now I put an inductor at the source, right? I ignore everything else upstairs because we don't know what we are going to put now yet. And we do it until the point that we need to put it, right? Because now I'm only interested in impedance matching. So let me only draw this circuit. So this is just a common source, right? Gate, source, drain. And then between the source and the ground, we add an inductor L1. So we went through the math. It looks sophisticated. But the main point is this: if we can do it by inspection, right? If you are very familiar with this, it actually is not difficult because we try to look at what's the value of Vx, because we want to know the input impedance Vx as a function of Ix. Then of course I know that it must be equal to the potential drop across the CGS1 plus potential drop across L1. And the potential drop across CGS1, just think it as an impedance, right? Like a resistor, follow Ohm's law. So this must be equal to Ix times the impedance, right? Just Ix times Z, right? The impedance. So as a result, we already have this term, which is Ix times the impedance is 1 over SCGS1. Because 1 over SC is the impedance of a capacitor, right? So if you are familiar with this, you can write this already. And then if, of course, it's equal to the total current going through L, the impedance of L is SL1, right? L1. The point is, what is the current going through L1? It's not just Ix, it's also the current Im. But we should know that Im, again, this is a transistor. I already know what is, if I already know what is VGS, I should know what's the drain current, right? It's connected through which parameter? If I know the gate source voltage, what is the current? GM times VGS, exactly, right? So that's why the total current, yeah, Ix plus GM times VGS, which is just Ix divided by SCGS1, because Ix divided by SCGS1 was just the VGS that we just discussed, right? So if you're familiar with this, just this one line, you already can relate Vx to Ix. We did the math, then we came up with this. Now this can be confusing to some of us, to myself also, maybe in the beginning. But the main point is this: the impedance has two parts. This part has S, so it's J omega. So this part, these two terms, are the imaginary part. However complicated it is the imaginary part. It also has this part in which the S got cancelled, so it's purely real, right? And that's why we are able to get the impedance to match to 50 ohm, because now this is a real part. And it depends on what? GM, L1, and CGS1. And this explains why we say this is inductive degeneration for input matching. Because we rely on this inductor to get the 50 ohm, right? And then later we got some confusion. So I came back to just remind you that this is Z-in. Yes, this is a complicated circuit. But once we got the formula, this is the expression of Z-in. Isn't that it just equal this impedance plus this impedance plus this impedance? This is given, right? It's just like that I solve a very complicated circuit and you tell me that the total R is R1 plus R2 plus R3. Isn't that I can just draw the equivalent circuit as one resistor R1 in series with resistor R2 in series with resistor R3? Make sense? Do you understand what I'm talking about? Yeah? So let me say it again, right? If I'm going to erase this because it's going to confuse it. If I solve a very complicated circuit and I came up with this, R equal to R1 plus R2 plus R3. Do not ask why I don't combine R1, R2, R3. But I just keep it that way. I came up with an equation like this. Isn't that its equivalent circuit is just this? R1, R2, R3. Do you agree? Even though originally this circuit has 1 trillion transistor or resistor in parallel in series, but I came up with an equivalent circuit which is R1 plus R2, R3. I can replace this circuit with this 3 resistor. Make sense? So similarly, here we solve a complicated circuit. We came up with Z-in equal to this impedance plus this impedance plus this impedance. If you look at this carefully, this impedance is 1 over SCGS1. Isn't that it's just equal to CGS have a capacitor? And then plus SL1, the same, just having a L1 in series with the capacitor. And then plus a real number, let me call it R1. Then in series with R1, this whole thing is just equal to this circuit, right? Make sense? I'm not saying this circuit is this circuit. I'm saying that this circuit is equivalent to this circuit when I am considering Z-in. Right? This circuit has amplification. I cannot use this circuit to do amplification, of course. Right? When only talking about Z-in, then I can replace everything by this because I already proved to you this is the circuit. Make sense? Okay. So that is first thing. And at that time, so we'll come back to this later. Right? And that time we say, okay, then in order to get 50 ohm, then what? Then you make GML1 divided by CGS1 equal to 50 ohm. Then you are done. Right? But if we try to plug in the math, we realize GM divided by CGS is just the transit frequency, omega t, that we learned quite a long time ago. That is kind of the maximum frequency. You still have a unity current gain for a transistor, right? Which represent maybe the highest speed a transistor can switch. So usually this is pretty large. For example, 65 nanometer is 160 gigahertz. You go to 28, it's even larger. Then you make your L1 to be pretty small. So in reality, we will just use a bond wire to connect this to the ground. This is a very small bond wire, right? If you want to have a large inductor, you are going to have a lot of turn in the inductor, right? Here it's just a very tiny piece of metal, and then it will give us enough of inductor, and actually more than enough, unfortunately. Okay, so this might not be a solution. And here again, if you can understand this drawing, then you know what you're doing as a circuit designer. Here is just the transistor M1. You have the source, and middle is the drain. We call this a multi-finger structure. We talked about this earlier. In order to reduce the gate resistance, instead of have a very wide equivalency, this has two times of the width you are seeing here, because this is just like two transistors, right? The current go from drain to the left, and then from drain to the right, and this source a connector. So you just like have two transistors in parallel. This is like finger layout, multi-finger layout. Forget about the name, interdigit layout, okay? And this is the source. Any questions? Not about the math, but about the concept. Is that okay? Okay, now, then we try to review some basic information, right? Because we need to understand how the pad capacitance is going to affect the impedance we are going to match, right? So first of all, we say that if I have a resistor here, pure resistor, and then I have an reactive element, either capacitive or inductive in series. Looking into here, we actually can make an equivalent circuit so that this is in parallel. In order to make it in parallel, you need to change the resistor, right? So basically, what we're doing here is just say that this series circuit is the same as this parallel circuit when we have the same reactive elements, still X1, but we need to adjust RS to be RP. Okay? And what are their relationship? We went through some reasoning, but the main point is that Rp is equal to X1 squared divided by Rs. Rs is equal to X1 squared divided by Rp. So this is just a transformation. If you give me this circuit and ask me, make this parallel. Okay, I don't like series. I just don't like the word series. Can you make it parallel? Okay, I make it parallel. But in order to make it to have the same impedance, you need to change Rs to Rp through this equation. Questions? No, right? Okay. So why do we want to do this? Now, then we come to here. That is because of the effect of the pad, right? So as I just told you earlier, we derived in slide 5, right? This part from slide 5. This gives us the equivalent input impedance. Do you see this? Right? Okay. Now, but however, this is just bonding to the ground. For the gates, it also has its input pad because you need to put in the signal maybe from antenna from elsewhere, right? So last time I drew it, let me draw it again. Basically, it's like this. You might have an antenna. How do you draw antenna? Right? And this antenna will come to here, and then it's bound to the pad, right? This is the pad. And this pad will then go in, and then of course you are going to see the amplifier. You have CGS1, you have L1, like this. Do you see that? Right? That is what you have. You come in, see the gates, you have CGS1, and then you have L1. That is the real circuit. But this guy, this antenna, this pad itself creates a parasitic capacitor called C-pad. And of course, for antenna, it also has a 50 ohm, which is not 50 ohm, sorry. Let's assume it's 50 ohm, right? Let me don't write it. There will be some transformation. But anyway, so it's okay. And that's why we have this circuit. And now the question is, okay, fine. You derive this equation and you try to set R1 equal to 50 ohm. Did you really match the impedance? if I have a CPAD here. And that is the goal. My goal is to transform this to here and then eventually figure out what is the real impedance I see. Is it really R1, which I set to 50 ohm, or is it something called R equivalent? Okay, so let's do this step by step. But do you understand our purpose? Okay, thank you. Okay, so first I'm going to say, okay, let's, yeah. Very good. Our goal is that because of this CPAD, we want to make Z in the real part of Z in 50 ohm, which is R equivalent equal to 50 ohm. Yeah, we will cancel imaginary later, but the real part need to be 50 ohm. Yeah, very good. But now I'm not trying to make it. I try to show what is the relationship between R equivalent and R1, right? And if you already know what is R1, then you do something, then you can make R equivalent 50 ohm. Okay, so just for the sake of simplicity, I just saw JX1, which we discussed earlier, JX1, right? I want to study this. I call it equal to J omega L1 minus J over omega C, no, J omega CGS1. So basically what I'm doing here is that I call this whole thing JX1. Is that okay? I just combine that. Of course, it's very complicated because this is capacitive, so it becomes negative because it should be 1 over J omega CGS1, right? Plus 1 over J omega CGS1. So it becomes minus J over omega CGS1, right? So this is JX1. Now, why do I want to do that? Because then we can use the equation we learned earlier. And then, of course, I call JX2 equals to negative J over omega CPAD. So I'm talking about this one. Now I call it JX2, just to make things easier, right? So with this, then of course the circuit can be viewed as, no need to do this, right? I already have the circuit here. Don't waste the time. Oh, not yet, actually, sorry. Then the circuit becomes, how will it look like? It will be parallel JX2, right? And then JX1, and then R1. So, okay, so this is the first circuit, and this is the second circuit. But they're equivalent. I just relabeled them. Okay. Then I'm going to do transformation. Right. So in order to do the transformation, the first thing I transform this guy first. Right. Remember, series to parallel, right? So I decided to make it parallel. So I have JX1, X2, I don't touch it. Then I put JX1 here. But now I need to change my resistor here. It's no longer equal to R1, it's equal to RP. And what is RP? Do you remember the equation? Very good. Do you remember the equation now I'm showing you? X squared over X1 squared over R1. Right? So RP become X1 squared over R1. So what I'm trying to say, this circuit is the same as this circuit if I replace R1 by RP equal to this. Okay, then this is actually just the circuit 3 that we are showing here. Right? Then of course you probably already see that this one I can just combine the two parallel elements, right? Yeah. So this becomes J should be negative. Should be no. This becomes J X. My cheat sheet is wrong. So it should be the square of J, right? Jx. Let me write it elsewhere. So I come back. Because it looks like I have some problem with my cheat sheet. Jx1, Jx2 divided by Jx1 plus Jx2. Right? That's the parallel. So my cheat sheet is right actually. Then it's equal to what? J x1, x2 divided by x1 plus x2. Is that okay? Just parallel resistor, right? So this is J x1, x2 divided by x1 plus x2. And then this whole thing, RP. Right? I did not do anything. I just combined them. Why do I want to combine them? Because with this, then I have this circuit, right? I can bring back to this series circuit. Again, what is this series circuit? So this becomes 5. Circuit 5. I bring this to a series circuit. And now this is our equivalent. And of course, I will keep the reactive component, Jx1, x2 divided by x1 plus x2. Correct? But what is our equivalent? The square of the impedance, right, over Rp. So which is x1, x2 divided by x1 plus x2. This is the value of the reactive part divided by Rp. Right? But we know what is Rp though. Rp is just x squared, x1 squared divided here, x1 squared divided by R1. So let's just plug in. Then here I get x1 squared, x2 squared divided by x1 plus x2 squared, right? And then times, and divided by Rp will be times R1 divided by x1 squared. So x1 got cancelled, right? So eventually, we have R equivalent equals to x2 squared R1 divided by x1 plus x2 squared. It's all math, but just a practice. You need to do this very often, right, in RF circuit. Right? And of course, this is the 5th circuit also. I did not label it. I mean, eventually, with this, so all this thing is to realize, is just to say that, okay, for this complicated circuit, it's just the same as this simple circuit with our equivalent equals to this. Now, the message is, if you already match R1 equal to 50 ohm, your real part of this circuit due to this CPAD is no longer 50 ohm. It's 50 ohm scaled by this. So if you want to put this 50 ohm, then it means you need to adjust your R1, which depends on GMC, GS1, and L1. Is it okay? Okay, so in summary of this page is just to say, I have the CPAD, right? So now it's CPAD. In case you do something special in your circuit, you might have additional capacitor, parasitic capacitor. You do the same thing to adjust it so that you get what you want, right? And we get this equation. So with this, then we can try to estimate how much the CPAD is going to impact the real parts of the impedance. Now, so what is x1 plus x2, right? Because the equation tells us that it's scaled by x1 plus x2. But x1 plus x2 is this quantity. Okay, so let's just write it down. You trust me? Otherwise, you copy from the previous page. It's just J, this one. Is omega L1 minus 1 over omega CGS1 minus 1 over omega CPAT, right? Omega L1 minus 1 over omega CGS1 minus omega CPAT when you add x1 and x2 together, right? This is what you have. Now, I'm going to do approximation. If omega L1, right, is much smaller than 1 over omega CGS1 plus 1 over omega CPAT. Right? This is an assumption which depends on your operating frequency. But let's say omega L1 is much smaller than that. And that makes sense because remember, our L1 is pretty small because of what we are trying to match. We need to pick a small L1, right? So it actually, usually it is smaller, right? Then the reason we do this approximation is make our life easier. But now you have Excel, MATLAB, Python. You can always just do the exact solution. So what is the factor that is used to scale R1? Remember, this is the factor x2 divided by x1 plus x2 squared, right? We're talking about their magnitude. So I care about their magnitude. Then I plug in. x2 is 1 over omega CPAT. x1 is 1 over omega CGS1. And x2 is again 1 over omega CPAT. Then you multiply the denominator and numerator by omega CGS1 and omega CPAT. Then you cancel the omega. Then, of course, you get CGS1 divided by CGS1 plus CPAT. So this is the factor. Okay? So it means that the R equivalent equal to CGS1 divided by CGS1 plus CPAT square times R1. Which makes sense, for example, right? As an engineer, always try to check the extreme case. For example, if CPAT equal to 0, it means I don't have parasitic capacitor. Then R equivalent equal to R1, which makes sense, right? We did all this is because we have CPAT. If we didn't have CPAT, that is exactly what we had at the beginning, 2 slides ago, right? So if you can reduce the CPAT, then your R equivalent will be larger, right? If you reduce the CPAT, okay? Now, if, let's just say if CGS1 is in the same order of CPAT, then what will happen to R equivalent? If they are similar, let's say they are the same. What is the expression now? 1 over, 2, 4, 1 over 2 squared. So it becomes R1 divided by 4. So this is actually good news because now we can have 4x larger L1 to get 50 ohm. Right? Because R1 is proportional to L1. Right? In order to get 50 ohm, here I need 50 picohenry. But now it's not the R1 that determines the real part. It's R1 divided by 4 determine the real part. Right? So I can make R1 200. Right? then the equivalent will be 50. Make sense? So that helped me to do the impedance matching. So the constraint will be smaller. But the main point here is to learn this circuit technique. You can always use simulation, but if you don't know what's going on, like in the project, right? Some of you at the beginning just keep changing the wave, changing the inductor, and then changing the resistor, right? Once you match the real part, then the imaginary part is off. Once you match both, then the transistor is in linear mode, right? Then you can never get it done. You really need to go through the theory to guide you, okay? Any questions? Okay, so then let's go to the summary of this paper. Again, this paper is too difficult for this class, but the point is that now you already learned how to do the common source with inductive degeneration. We use L1 in order to get R1. And then because of the pad, we actually can change R1 to something larger than what we need. Then we have 50 ohm here. But with 50 ohm here, we still have the reactive part, right? So that's why we will add LG to compensate. LG is the, right, this is to compensate J x1, x2 divided by x1 plus x2. Compensate this imaginary part. So with this, then we are done, right? We get a pure 50 ohm. This is pretty beautiful. Such a complicated circuit, it will give me, I will only see 50 ohm of resistance, right? RS is just the source, right? Now, but usually this LG is pretty large. So usually you use off-chip, right? A large one. So for this paper, it improved noise figure and many aspects because what do? They have a fully integrated LNA. The large inductor, right, is discarded. They did something. I forgot what it is. Let's take a look, right? So that they don't need this very large off-chip inductor. That's one of the main selling points of this paper. Okay? But assume we don't care about this, but now you know how to do this impedance matching if you really want to design a chip, right? You think about the whole thing. Any questions? To remove the inductor? I forgot. You need to read the paper. I did not read it this time for this class. Yeah. Okay, so done. So we match the input impedance. What else? We found the input impedance, and now we match the input impedance, right? Which is pretty good as an LNA. Now, but more importantly is to know what are the noise and gain, right? So we'll start with the gain, right? Why do we need to know the gain in order to calculate the noise? It will appear in the final exam, right? Why do we need the gain to calculate the noise? Yeah, because I should say not noise, the noise figure, sorry. Yeah, because you need to normalize to the gain, right? I mean, you need to divide by the available gain and then divided by the not available power gain. That is a Fitz's law. I mean, divided by the total gain square and then normalize to the source impedance, source noise, right? Thermal noise. Then that is the noise figure, right? So we need to know the gain. So on the right is the circuit. So what is the gain? Now, this is, let's just draw the small signal model. Very simple. You should be able to draw it, right? If I actually can put this in E124 exam, everyone should be able to draw it, right? They even can solve it, right? It's just that they don't know what all the profound theory or utilities of this special circuit behind, right? So let me draw it. The first thing, always just draw the small signal model first. So I try to draw everything. Plus minus VGS. So this is what? GM, VGS. But this is RF circuit. I definitely need to draw. See, what is this capacitor? GD. I also have this capacitor. What is that? CGS, right? I also have others, but I don't want to draw them because I'm going to simplify them, so I'm not going to draw them. That is the first thing. Second thing, then let me connect the circuits. What do I have here? Source is connected to what? L1, thank you. How about the gate? Now, do not get confused by this part. These are just the equivalent model, right? For input impedance calculation. So you don't see this. What you really see is this one. You already have CGS. What do you see when you go to the left? V in and CPAD and LG. Right? These are real, right? LG to compensate your imaginary part. CPAD is there, right? So I'm going to draw CPAD. This is the real thing, right? This is the circuit you have after you do the impedance matching, LG. And yes, you have RS, and then you have V in. Is this okay? Are you okay with this circuit? Now, on the right, I did not draw it because I did not put the LG here yet, right? I used, maybe next time I should just put this circuit there, then it will be clear, right? We do have an LG after the matching, right? So I need to say this is after Z in matching, right? After I did everything to match the pure impedance. Is that okay? And then now is my authority because I have all the right to do simplification because I give grade, right? So I just follow the textbook. We just ignore CPAD. We also ignore CGS. I also ignore R0. Just ignore for simplicity. Right? Is that okay? I just ignore them, take them off, right? I still have one problem. How about the drain? I need to solve the gain, but I don't know where's the output. How can I solve the gain? You have no idea. Because the output is not drawn. Definitely it's not floating, otherwise it's useless, right? So you really don't know. But we are going to make an assumption. We assume it is grounded. Why? You will realize why later. Grounded because we will use this in a Cascode circuit where that means you look into the source of a transistor. So you get 1 over GM, which is small. Okay, the only reason that I dare to ground it is because for the later use. Now, I even find the gain is useless for you, right? Because you still don't know the whole circuit. So this is just a part of a bigger calculation. And later you realize that what I make here makes sense. If you find that it doesn't make sense, then you better go back to redo your calculation. Do you see what I mean? Why I ground it? Just because I know that later is C very small output impedance, which is about 1 over GM. Yeah. Yes. Yes. So maybe I should show you what a Cascode circuit look like first, right? So later I'm going to put this like this one, like what you did in your LNA, right? So in your LNA, you look up, this is 1 over GM. 1 over GM is small, right? If you want, you can put 1 over GM as the load, but it's complicated. It makes the calculation complicated, right? So we say just approximate it as grounded. Right, so I want you to be very clear why I do this. I do this because I already know that later this is going to see a very small impedance in the load. This is the load for this circuit. If you only look at this part, looking up is the load of this circuit, of this part of circuit, right? As an electron coming out from the drain, what you see is the source of M2. And we already know that looking into the source of a transistor is 1 over GM, which is small. And indeed, it's pretty small. Remember in your Cascode circuit, in your LNA, right? Many of you design 20 micrometer, right? Where, 50 ohm, maybe larger, approximately 50 ohm. 50 ohm is small, right? In that sense. Okay? So that's why I dare to do that. Now with this, then the rest is just math, right? So then let's start with the math, yeah. So what is the gain of the circuit? Now what I care about is the output, right? Again, you may say that why is the current as the output? Just because later we use the current as the output in the circuit. So that's why you use that. You cannot use voltage because it's grounded, right? So the gain is I out divided by V in. That is the gain that we are looking for. So this is what type of amplifier? Transconductance amplifier. If you don't know that 5, you can look at the E124 video, but basically you can have input as voltage or current, output as voltage or current. If input is voltage, output is voltage, there is a voltage amplifier. If input is current, output is current, there's a current amplifier. If input is voltage, output is current, so it's a conductance, right? But it's trans, because they are not at the same terminal. So it's called transconductance amplifier. If input is current, output is voltage, then what do you call? Input is current, output is voltage. Transimpedance amplifier, because the gain is voltage divided by current, right? Here is the gain. The gain is output current divided by input voltage. So it's transconductance amplifier. So let's start working on this, the math. Let me see, I should just be careful of the page. So what is I out? So the I out, you just look at the KCL. Is equal to GM VGS, right? And I'm sorry, I actually need to add because we're calculating the noise also. I need to add, instead of, color should I use this one? Right, I also need to add a noise source, IN square out. IN square. This is the noise due to the transistor, right? What is the noise? IN square bar, what is that? Remember? 4kT gamma GM. Very good. Okay. Now, so what is I out? Now, because I include the noise, because I want to do it at the same time. I have not do superposition yet. So I just say total I out equal to IN1. Let me call this 1. Of course, this is just the math, right? Because I really don't know exactly what N1 is. I only know the power spectral density, right? But in terms of current, it is IN1 plus GMVGS. It's just saying that your output is not just due to GMVGS, it's also due to the noise that you have. Right? Basically, if you don't have output, you still get output noise. Right? That is the meaning of this noise source. Right? So let's start with, we will just continue, solve both at the same time. We use KCL, we look at V in. right? What is the V in? V in, of course, is just equal to potential drop across RSLG, potential drop across CGS, potential drop across L, right? So this is equal to what? First of all, I'm going to represent it as the VGS because VGS is an important variable. So the current, maybe it's better, I don't have this in my cheat sheet, but better to say that, right? The current I in, or maybe let me do this. Let me just say, what is VGS? We learned that before. VGS equals to I in divided by SCGS. Because the potential drop across this is equal to current times the impedance. The impedance is 1 over SCGS. Right? That is exactly what we did earlier. Remember, what we repeated earlier. Current divided by SCGS, right? And the reason, of course, you need to go through all this. You probably have a lot of troublesome if you do it from scratch. I just copy from the textbook. Of course, it's trivial for me. But anyway, then, so what does it mean? What is the current? Then it means I in equals to VGS times SCGS, right? So that's why VGS CGS times S, which is the current, times RS plus SLG. Give me the potential drop across this guy. Because this is the current, right? Current times the impedance. And then plus, then I'm going to just put VGS. Of course, this is VGS, right? VGS across it. And then what is the potential drop across RL? Now, RL, the impedance is SL1. But what is the current? Well, the current, you have two parts. One is the part coming from input, right? From R in. Another part is coming from here, right? Okay? So because of this, this is equal to, I'll just put I out plus, again, this is the current VGS CGSS. Do you see what I'm doing? This is I out. Yeah, it will go through different branches, but anyway, all this I out will merge here anyway, and they will go down here. And this is I in, right? Maybe I can just highlight that. This is I in, right? So I out plus I in, they all go to L1. So times SL1 will give me the potential drop across this, which is Vs. Okay? Now with all this, then I can come up with the equation. I can simplify it. I could get V in equals to, I have I out, LS1 SL1, sorry, I out SL1 or L1S, right? This is the whole thing. So V in equals to I out times SL1, right? And then each of these terms has VGS. I'm going to take out VGS. So I have VGS, this whole thing. Maybe let me put it at the end so that it'll be easier to see later. I take out VGS. So here, what do I have? I have CGSS times RS plus S square CGSLG, right? So what I'm doing here is multiply this term into, I'm going to take out VGS at the end, okay? So I have CGS times RS, CGSS times SLG. That's why I got S squared, because I have two S, right? And then what else? Plus 1, because I said I take out VGS, right? And then here I already take out I out SL1. So here I only have S square L1 L1 S square L1 CGS. And then the whole thing multiplied by VGS. Sorry, this is a little bit confusing, right? So let me repeat what I'm doing. You agree with this equation? Then I have SL1 times I out. I put it here. Then for each of this term, I take out VGS. Right? So this term, I will get CGS S times RS. CGS squared times LG. And then this term is 1. And then the last one, take out VGS, I have S squared L1 CGS. Okay? So with this, I continue to keep this term I out SL1, right? And then I will just do some factorization. I'm going to take out the, because you see all this term has SCGS, SCGS, SCGS. So I will just take out SCGS, the whole thing. Then I have RS, right? Plus S, here I take out SCGS, I still have SLG. Here I take out SCGS, I still have SL1. So this is just SL1 plus LG. Make sense? The last thing is I need to substitute VGS from this equation. And what is VGS from this equation? It is just equal to I out minus IN1 divided by GM. And this is from equation 1. Right? I have VGS. I just substitute VGS as I out minus IN1 divided by GM. Very complicated, and sorry for this confusion, right? But at the bottom, how do I avoid? I don't know how to avoid. But at the bottom, I show you what it is. It's exactly the same as I out. This is L1S plus all this term. And then I out minus IN1 divided by GM. Right? Sorry for this confusion, but just go back to try. The main point here so far, what we have done is that we understand, we try to draw the small signal of this circuit. And this circuit is for the one that you already have impedance matching. We enumerate those we can ignore. In your real project, your real design, you know that you can ignore because you know they are too small or too large, or based on your experience, or you want to simplify it. Another important thing is we ground the output. The reason we ground it just because we know that later this is going to drive a low impedance load, which is going to the input of the source input of a transistor. And then the rest is just solving KCL, KVL. The goal is to get V in as a function of I out and IN1. Because by doing this, I will be able to get a gain. Okay?
So for the KVL at the output, so did you assume the
Yeah, so this is a good, actually, we don't need to assume any direction. You can use plus minus because later our goal is not really to know the real value, right? Our goal is to calculate the power spectral density. So you can assume for the noise, you can assume it in any direction when you plug in this type of equation. Okay, so so I assume that is actually I draw it up, but actually in my equation it's going down, right? So it doesn't matter. Say again. Cancel. Oh, we are not there yet. Here we just draw the general relationship when you have both V in and the noise source. After that, we are going to use superposition. We will turn one of them off one by one, get the result for what we want to do, right? So now we are not doing the gain, right? We have not finished computing the gain yet. And for the gain, you should not have the IN because the gain has nothing to do with the noise. Yeah. So I copy here, right? So good question. So now let's start doing something exciting. Now, however, what is this one? SL1 plus S plus LG, right? But at the resonance, right? At resonance, we have 1 over square root L1 plus LG CGS1 equals to omega naught. Because I mean, I don't have the full circuit. This whole thing is replaced by this one, right? We ignore the CPAD, right? So RLG is used to cancellate the impedance, the inductive, the reactive part. So when we are operating at the resonance means at, right, at Z in matched, which is means we have we have only real part. This is equal to omega squared. So it means what? Then it means L1 plus LG times CGS1 S squared plus 1 equals to 0, which is this term. This whole term is 0 at resonance. Let me just remind you again, right? Remind you the circuit. The circuit is, we have LG, and then we have L1, and then we have CGS1, and then we have R1. When we ignore iPad, right? Ignore CPAD. Ignore CPAD. Is this okay? Remember, this is the equivalent circuits when we look into the input of the LNA. At the beginning, I told you it's just L1, CGS1, and R1, right? And without the CPAD, we just need to add LG to cancel out these two terms. Then you have R1 equal to 50 ohm, right? So then it means that this got cancelled. Then it means that this term is equal to 0. So the good thing is that now this is simple. This whole term is gone. Okay, so let me write it again. So V in now equals to I out. I group them, right? I out L1S. I out L1S. And sorry, actually, I want to make it into J omega 0. J omega 0 L1. This term, SL1 is J omega L1, right? And then this term is gone. Then I only have this I out, so it is plus J omega 0 RSCGS1 divided by GM for I out, right? Because I out J omega 0 CGS1 RS divided by GM. Done, right? But I still have this IN1. Okay, I just separate that, which is times J omega 0 RS CGS1 divided by GM, because it's the same term, right? This whole thing, this part is gone, so I only have this term, right? So they have the same term. Right, so what we have done is just to express V in terms of I out and IN1 at the same time at resonance. Right? We know that we design it, we only care at the frequency that we want, right? Our operating frequency. Then we are going to do it one by one. Okay, now, when no noise. When there's no noise, then of course IN1 equal to 0, right? So what is the gain? The gain equals to V in divided by I out. And we only care about the I out divided by V, I'm sorry. Very good. Is equal to I out divided by V, right? Which is equal to a pretty complicated, is 1 over the whole thing. 1 over J omega 0 L1 plus J omega 0 Rs CGS1 divided by GM. Is that okay? But I'm only care about the magnitude because later we're going to square it, right? We're going to find the magnitude anyway, right? So the I out divided by V in, but the J is gone, right? So it is just equals to, actually I need to do some more math. Let me just write this down first, right? It's equal to, you have omega 0. 1 over omega 0 L1 plus RSC GS, don't need math, CGS1 divided by GM. Right, so what I'm doing is just take the magnitude because this purely imaginary J is gone, and I take omega out, so I only have L1 here plus RS CGS1 divided by GM. And of course, this is RS divided by omega T also, right? But that's okay, we will think about that later. Is that okay? Any questions? So we'll continue to simplify it. Now, one more thing. Since Vx divided by Ix, what is that? What is Vx divided by Ix? Is equal to 1 over SCGS1 plus SL1 plus GML1 divided by CGS1, right? This is what we matched earlier, right? This is the Z in. What's the slide? Slide 5. Then what does it mean? Then it means RS equal to GML1 divided by CGS1, which is equal to equal to L1, omega T times L1, right? Right. The reason I want to do this is just to show you that this term is RS times CGS divided by GM, right? So that means the gain. Can you see that already? The gain or the magnitude of the gain is equal to 1 over omega 0 L1 plus, let me just plug in RS. What is RS? GML1 divided by CGS1 times CGS1 divided by GM. Go to what? 1 over 2 omega 0 L1. Yeah, and the reason I got confused is because I don't want to express as L1. What is L1 in terms of Rs and omega t? Rs divided by omega t, right? That's why I need to plug in L1, then I get omega t divided by 2 omega 0 Rs. So I actually should not replace it by L1. Actually, I should just use CGS divided by GM, which is equal to omega t. You don't get it? Okay, so let me redo it, right? I'm very sorry for all this confusion. Let me redo it, then it will be clearer. So I will get the same answer. So I went through a route that is confusing to you. Are you okay with Rs equal to GML1 divided by CHS1? And I remind you, GM divided by CGS1 equal to what? Omega t, right? The transit frequency. GM divided by CGS1. Are you okay with this? That's what we studied earlier in slide 5. Right? GML1, CGS0, omega t L1. Is that okay? So my goal is to remove L1. So from here, what is L1? L1 equals to Rs divided by omega t. L1 equal to Rs divided by. Is that okay? Then what I'm going to do is just substitute L1 to this equation. Okay? So L1 equals to Rs divided by omega t plus Rs divided by omega t, because GM over CGS1 is omega t. Okay? And you add them together, then you will get omega t divided by 2Rs omega 0, which is the same as what I gave you earlier. And that's the reason I got confused. I wrote this cheat sheet a long time ago, so sorry for that, but I hope that this make it a positive experience when you see how I make the mistake, or from different direction, you see you get the same thing. The goal is to eliminate L1. Okay? Any questions? Now, so with this, then the next step is to do the noise, and then we will be able to calculate the gain, right? But we are pretty good, actually. I will stop here. On Wednesday, we will do the presentation, and then next week I will quickly finish the rest, and then we will review some of the content, and then have final exam. Okay. Sorry for this confusion. Thank you.